Hi, everyone. So welcome to the first webinar of Global Forest Watch's new series, Frontiers in Forest Monitoring. My name is Alice Gottesman, and I'm GFW's User Outreach Specialist. Today we'll be presenting on satellite monitoring, providing you with a foundation in remote sensing technologies. Before we get started, I wanted to give an overview of how you can ask us questions about the webinar or communicate with us if you're having technical difficulties. If you have a question about what we're presenting, please click on the Q&A button and type it in there. At the end of our presentation, we'll have some time to answer questions that were typed into that section. If you're having technical difficulties, please communicate directly with us through the chat button. Please note that we will not be closely tracking content-related questions placed in the chat section, only in the Q&A section. So put more simply, the Q&A is for questions and the chat is for technical difficulties. So let's get started. Our presenters today are Michaela Weiss, a manager at Global Forest Watch, and Kai Krezek, Global Forest Watch's data specialist. Michaela leads GFW's strategy and partnerships for satellite-based forest monitoring. She has a particular interest in on-the-ground use of early warning deforestation systems and leads GFW's engagement with law enforcement. Kai works to streamline and manage the process for updating and incorporating data into the GFW platform and associated applications. So the goal of the webinar today is to provide you with a foundation in satellite imagery and remote sensing concepts so that you can achieve a deeper technical understanding of how our forest change datasets are created and analyzed. Future webinars in this series will be intended to dive deeper into these technical aspects. So GFW offers an integrated, openly accessible suite of tools designed to enable experts and non-experts alike to access information about forest change and mobilize action. Some high-level examples of how this is done include increasing knowledge and transparency about forest landscapes. GFW tools and data offer access to the state of the world's forest to everyone, everywhere for free. Harnessing information to mobilize local action by governments and civil society. We have a variety of partners and some programs that help promote data-driven action. And finally, advancing private sector action to stop commodity-driven deforestation and manage forests sustainably. One of our tools, GFW Pro, allow the private sector to measure risk associated with their supply chains. Here's an example of what you can see on the GFW platform. This particular dataset is the near real-time GLAD deforestation alerts. The GIF visualizes as tree cover loss spreads, indicating a new logging road entering a national park buffer zone in Peru. So why monitor from satellites? There are a number of key benefits that satellite monitoring offers, including satellites comprehensively cover large areas and provide a global look at fundamental climate measurements, including deforestation. They allow us to easily compare different areas since it covers large areas and the data is consistently measured. Satellites orbit the planet for years, meaning they repeat observations regularly. They can therefore make consistent measurements over long periods of time, providing an accurate reading of change. Because space is the vantage point, satellite monitoring allows us to view and measure change in places that are difficult to reach. Lastly, several governments now offer free imagery from satellites, such as Landsat through NASA and USGS, as well as the European Space Agency data, and many more. So moving forward, we'll dive deeper into optical satellite imagery, other types of satellite imagery, and lastly, how to access and interpret satellite imagery. I'll now pass it off to Michaela.
Great, thank you, Alice. So I'm just going to go over some of the basics of how satellite imagery works. And then in future installments, we'll talk about how we actually create some of the data sets on Global Forest Watch using this type of information. As you may know, there are hundreds of satellites that are orbiting the Earth every day. The video that you see now is of the NASA Landsat Satellite, which is orbiting the Earth around every 16 days. So as you can see from the video, when it's going around the Earth, it's capturing these what we call swaths, right? So these thin strips of area that it's actually able to take images of. And, over the course of 16 days, it's actually, circling multiple times and able to capture every point on the Earth's surface around every 16 days. So how this works essentially is that the energy that's emitted by the sun comes down to the Earth's surface, right? That's similar to what we see during the daytime. And then that's actually reflected back up through space to the satellite, which captures that information and then sends it down to a ground station before it can be used by people like you and me. So I'm going to get a little bit into physics. So hopefully you remember this from your high school physics class, but here's just a bit of a refresher. So the light from the sun is emitted all across the electromagnetic spectrum. So this small area in the middle is where we actually see visible light, right? So this is what's visible to our eyes, and we know that different colors are different wavelengths on this electromagnetic spectrum. But the important thing to keep in mind here is that there's actually a lot of energy that's emitted from the sun that is either shorter wavelengths or longer wavelengths that our eyes can't actually see, but in many cases can be detected by satellites and gives us a whole lot of extra information about the Earth's surface. So just, again, thinking about how our eyes visualize light, we know that, all different colors of light are coming down to the Earth's surface. And then actually what we see is the light that is reflected by that object. So a red object is actually going to absorb green and blue light, and red light is reflected back. And so that's what we see. Similarly, if we have a green object, that's going to absorb the red and the blue light and reflect back the green. And so our eyes can tell us something, about what kind of light is reflected, and a satellite can do something very similar. This figure is a little complicated, but bear with me, I'm going to walk you through it. So on the x-axis here, we have the electromagnetic spectrum that I showed in the previous slide. Here you can see, the visible spectrum from purple to red, what our eyes can see. And then everything beyond that is what we call infrared, which again is emitted by the sun and reflected by the Earth's surface and can actually be picked up by satellites even though we can't see it. On the y-axis here is actually the amount of reflectance that different surfaces have. And so basically what we're showing is how these four surfaces, snow, rock, vegetation, and water, actually reflect at different wavelengths. And the important thing to note here is that these lines all look quite different from each other. They all have very different patterns. And so that means that if we are looking across the electromagnetic spectrum, which satellites allow us to do, it's actually quite easy to separate out different types of land cover. So for example, vegetation has a very characteristic signal in that, it has a little bump in the green, right? That's what we can see where, plants appear green to our eyes. But then it also has a very strong reflectance of infrared light. And so that's something that the satellite can actually pick up is a large difference between, what's occurring in the optical wavelengths versus what's occurring in the infrared. So to give you an example from Landsat in particular, the way that this works, the satellite's not actually looking across the entire electromagnetic spectrum, but rather it has what we call bands. So you can think of this kind of like a camera, right, is capturing blue, green, and red, similar to our eyes. But in addition to that, the satellite is also picking up a few bands of infrared at these points in the electromagnetic spectrum. And so again, I have the vegetation curve here with that little bump in green and then a lot of reflectance in the near infrared. And again, by comparing this second band, which is the green, the third band, which is the red, and the near infrared, which is this gray one here, we can actually start to capture what those different reflectance signatures look like. And just to show what this looks like, so here's, a picture of a river and some trees, just a normal photograph similar to what our eyes would see. If you could actually see infrared, it would probably look something like this, where, actually those trees are reflecting a lot of infrared light, and so they show up as this very bright pink color in this image. So we can see something similar happen in satellite images. So this is just a satellite image from NASA. It's in true color, right? So it looks similar to how we would see it if we were up in the International Space Station. And you can see, there's these darker patches that are likely forests. There's these tan patches, which are probably deforestation. But actually, if we look at an infrared, an image using infrared, we can actually get a lot more detail. So here the infrared is shown in red, and so we see, this vegetation that's reflecting a lot of that infrared. That's why it's showing up red in the image. And then we also see these deforested areas in teal. But I think what's interesting about this example is that we also see a lot of areas in this darker color. If I just go back to the previous image, in this visible image, you can kind of tell that there's a difference between, this healthier forest and what I presume is a more degraded area, but it's not necessarily very obvious. However, if we actually look at the infrared in addition, then we can see really clearly where that degraded patch is, and we can also define a lot better exactly what the boundaries are of that patch. Switching gears a little bit, now we're going to talk more about spatial resolution, which is another very important facet of satellite imagery. Many of you are probably already quite familiar with this concept. If you've ever zoomed really far into a picture you take on your phone or camera or whatever, eventually you'll notice that you start to get individual pixels that are all just one solid color. And it's very similar with satellite images where, actually the images are built out of many, many of these individual pixels. The difference is that, since we're looking from so far away, those pixels end up being actually quite a large area on the Earth's surface. And so this diagram is showing an example of what you can see, what is picked up by looking at different resolutions. So in this top left corner, you can see very clearly these houses, looks like cars parked in the driveway. We can see individual trees. And in this case, our pixels are actually 0.5 meters by 0.5 meters, each of those squares. So we can pick up a lot of the details. If we go to the image below it, which is 5 meters by 5 meters, then we still can see the houses, we can still see some of the individual trees, but some of the detail is gone, right? The image looks a bit fuzzier, we can't really see the cars anymore. And if we continue to coarser and coarser resolution, so let's go to look at the 20 by 20 meter. This is similar to most of the satellite imagery we use on Global Forest Watch, which is 30 by 30 meters. In this image, we can still maybe make out some of the houses that appear a bit brighter. Some of that forested area might appear a slightly different color, but we're starting to lose a lot of those granular kinds of details. And then again, as you go on to 40 or 80 meters, then even less of that detail shows up. And so what this means for us and for a lot of the data on Global Forest Watch is that, most of the time we're not picking up changes in individual trees. Most of the time what we can pick up is patches, right, where a larger area of trees has been cut down or there's been a fire or something a bit more macro in scale. All right, so just to give you a sense of how satellite-based maps have changed over time along with the resolution. This is one of the first global land cover maps that was created in the 90s. I'll just zoom into one pixel here in the southeastern US. This is a 100-kilometer resolution pixel from 1994. And again, there's only something like 300 pixels in the entire United States. We're not getting a lot of the details. We can look at a wide scale and get a sense of the trends, but we're not getting very much detail. As things have improved over time, we've been able to use higher and higher resolution imagery to create these kinds of maps. So here's a few years later, looking at 16-kilometer resolution, we get a bit more detail. And then if we go on another 10 years, 1-kilometer resolution, now we can start to make out where there are cities, where there are, streams and rivers with riparian buffers, where there's agricultural land. But, we're still not getting incredibly detailed. Fast forward to more recently, and a lot of what we have on Global Forest Watch right now at 30-meter resolution, now we can get a lot more detail about, the shape of these cities. We can see individual roads that are cutting through these forested areas, and we can see these patches of agriculture that may be in different states or maybe mixed with trees on the landscape. And then going even beyond that, there are many private satellite imagery companies that provide even higher resolution imagery, although at a cost. And so this is an example from Digital Globe. This is 1 meter resolution imagery of the same area. And so now we can see, you know, not only the roads, but a lot more detail about how many lanes they might have. We can trace the individual buildings and we can see the individual trees that make up, you know, we can see this, these are in rows, so it's probably some kind of plantation or forestry operation. All right, and another important thing to note is that there is often a trade-off between the resolution of the sensors and how often the satellite revisits each point on Earth. So to give you an example of that, you know, if you were doing a ground survey of a large area, you can get really, really detailed spatial information about exactly where the trees are and you know, how much biomass they have. But you're probably not going to be able to do that very often, especially if you're trying to do every place. You might only get to it every 50 years or around that kind of a scale. On the other side of this figure, we have very coarse resolution satellites that are actually looking at the entire Earth and taking an image of it like every minute. They're zoomed out, if you will. So they're very coarse but they're taking images very frequently. And then somewhere in the middle, we find more satellites that are most appropriate for land cover monitoring that have what we call medium resolution, so 10, 20, 30 meters, meter pixels, and also can repeat that fairly often, once a month, once a week, somewhere around that scale. There are some satellites that are actually breaking this relationship between resolution and frequency. Most of them do that by actually having multiple, or in some cases even hundreds of the same satellites that are up in orbit, which allows them to take images much more frequently than this curve would suggest. So now I just want to get into some examples of different satellites and sensors that we find the most useful in our work at Global Forest Watch, give you a sense of what they are, some of the properties, and then also how we use them at Global Forest Watch. So the first is a NASA satellite called MODIS. It's been around for over 20 years now. It's somewhere medium resolution, 250 to 500 meters. But the benefit is that we actually get new images every day. So this can be useful for, you know, rapid change detection, kind of monitoring. It's freely available from NASA. And on Global Forest Watch, we use this data specifically for some of our alert products, namely some of the fire points and also the Terra Eye alerts that are tracking deforestation on a monthly basis. The next is Landsat, which I've already mentioned quite a few times. It tends to be the workhorse for many types of land cover monitoring. This is another NASA satellite, and they've actually had the Landsat program going since the 1970s, which is great because we have this historical record going back now almost 50 years of how land cover has changed over time. This is a 30-meter resolution satellite. So again, we're not picking up individual trees, but you know, definitely small patches of tree cover loss. And right now there are 2 of these Landsat sensors in orbit, and so we can get an image of each point on Earth around every 8 days. This imagery is also free, and it really is kind of the core of the data sets that are on Global Forest Watch. So the tree cover data, the tree cover loss and gain data, and the GLAD deforestation alerts are all relying on Landsat imagery. There's also a newer player in this space that I think eventually will reach similar level of usage, if not more, than Landsat, which is Sentinel II from the European Space Agency. So this was launched, the first one was launched in 2015 and the second in 2017. So a relatively new program, but it's a little bit higher resolution than Landsat, 10 to 20 meters. And with the 2 of them orbiting at the same time, it actually can revisit each point on Earth every 5 days. So there's a lot of development, a lot of scientific research about, you know, how to calibrate and you know, detect clouds within this so that you can create accurate maps. At Global Forest Watch, we are working on building a new alert system with the University of Maryland that would be comparable to the GLAD alerts, but a bit more frequent, a bit higher resolution. And we also have recent Sentinel II images available to view on the Global Forest Watch platform. All right, now moving into some of the private satellite companies. You may have heard of this company, Planet. They are known for having more than 100 of their PlanetScope satellites in orbit, which are quite detailed resolution, 3 to 5 meters. And because they have so many satellites, they can actually take images of every point on the Earth's surface every day. And again, having that quite detailed information daily can be very useful for looking at change and also for validating the change that we see in our, our forest change products that are built on free imagery. The downside, of course, is that this costs money, but we do have the monthly mosaics available on Global Forest Watch, which can be useful for getting a sense of, what's changing on a monthly basis at a fairly high resolution. And the last one I'll mention is Digital Globe. This is another private satellite company. They actually have a lot of different satellites within their constellation. They vary quite a bit in the actual specifications, but they tend to be very high resolution, about 1 meter. They can, in this image, you can see the shipping crates very clearly. You can count the number of shipping crates and see how big they are. The thing is that they are not, they do follow a consistent orbit, but they actually can point in a direction that the user wants. And so this means that, if you have a subscription and can pay for them to point in your direction, you can actually get quite frequent images. But if you're just relying on the images in the archive, they might not be as frequent or as reliable as one would like. On Global Forest Watch, we use this kind of information a lot for validation and training for some of our products. We do tree counting for some projects in monitoring restoration. And also some of this is available as like one of our satellite imagery base maps like you see on Google. So with that, I'm going to pass it over to Kai to talk about other types of satellite monitoring systems.
All right, thank you so much, Michaela. Hello, everyone. My name is Kai Kresick, and I'm a data specialist with Global Forest Watch. I'm here to discuss additional types of satellite monitoring systems. Thus far, we've focused primarily on optical satellite imagery, such as images produced by Landsat. These are also known as passive satellite sensors, meaning that they measure reflected light emitted from the sun. In this section of the presentation, we'll cover what are known as active sensors, specifically radar, also known as radio detection and ranging, and LiDAR, light detection and ranging. These systems are known as active sensors because they produce their own light to illuminate the surface of the Earth. I will walk you through how these different systems work, and we'll review some example systems that are in use in the field of forest monitoring. First, we'll cover radar, radio detection and ranging satellite systems. This image of the world was taken using MODIS, a passive sensor. As you can see, a swath of clouds are covering large portions of the forested landscape along the tropics and in the northern hemisphere. While optical satellite imagery is an excellent way to view the world as the human eye does, as well as to view the extent of healthy vegetation using the near-infrared range of the electromagnetic spectrum, there are some advantages, such as being able to see through clouds, that make active sensors such as radar a good choice for forest monitoring. Radar data has many advantages over optical imagery. As stated previously, radar is an active sensor, meaning that it creates its own illumination. This means that it can operate 24 hours a day because it doesn't rely on the sun to light the Earth's surface. To think of it a different way, we can draw a comparison between radar systems and other active sensors, and something you're all probably familiar with and may even have in your own back pocket. Cameras with the flash turned on are active sensors. In low light situations, you can use the camera flash to illuminate your subject, making it easier to see in the resulting photograph. Additionally, radar can pierce through clouds. Clouds are especially ubiquitous in the tropics due to a combination of warm temperatures, high humidity, and high precipitation. Clouds cause data quality issues in optical imagery that radar imagery can overcome. As you can see on the right image, there is an optical image on the top and a SAR image, so a radar image on the bottom. So there's a lot of area on the top image that's covered by clouds. However, the bottom image does not show these clouds and can instead penetrate to the ground surface. So radar is also sensitive to rough surfaces such as trees and other vegetation, as well as soil moisture content. We'll go into more about how SAR can do this in the future, but I just wanted to be specific. So synthetic aperture radar, which I've been referring to as SAR, is a specific form of radar. And SAR uses the motion of the radar antenna over a target region to provide detail at high spatial resolutions and is widely used for monitoring the land and sea. To create a SAR image, successive pulses of radio waves are transmitted to illuminate a target scene, and the echo of each pulse is received and recorded by the satellite. The pulses are transmitted and the echoes received using a single beamforming antenna. SAR measures the amount of radio backscatter or return signal the sensor receives. The amount of signal that returned to the sensor, also known as backscatter intensity, depends on several ground characteristics, such as surface roughness and water content. We'll go into more detail in the next slides. So this is a simple diagram of an optical sensor. So the satellite is on the top right, and you can see that the energy that's being emitted by the sun cannot escape through these clouds and come back to the sensor. That's why in optical images, a lot of the interesting areas that you're trying to look at are obscured by clouds. Whereas a radar system can penetrate clouds, such as this diagram is showing. The satellite on the top right is emitting that red beam, which I'll refer to in the future as the pulse. When it hits the ground, it returns as backscatter. So think of it, the energy going down is the pulse, and the return is known as backscatter. This will be important. So this is an example of how radar can illuminate the differences in soil moisture. Right here, you'll see that the surface affects the amount of scattering. The amount of scattering by the targeted terrain is influenced by both surface roughness and the target's moisture content. Less moisture leads to higher scattering. For natural surfaces, an increase in moisture correlates to an increase in conductivity and is associated with an increased radar reflectivity. Thus, wet soil, such as these areas marked with a W right here, appear brighter than dry soil or soil that contains ice. So the dry soil is labeled by the D and is right here. This sensitivity can be implemented in soil moisture studies and permafrost monitoring. So this next diagram shows a version of backscatter called diffuse backscatter, and this occurs when the radar signal encounters a rough surface like dirt or vegetation. The rough surface scatters the radar signal in many different directions, as you can see in the diagram here, and a small portion of it is returned to the SAR sensor on the top right. This type of reflection results in moderate levels of backscatter and appears as medium gray areas in a SAR scene. So here's an example of diffuse backscatter on a rough surface. It is surrounded by this white box right here. The next example I'll give you is specular backscatter, which occurs when a radar signal reflects off of a very smooth surface, like water or pavement. The smooth surface reflects the radar signal like a mirror, sending most of it away from the SAR sensor, as you can see in this diagram. This type of reflection results in low backscatter and creates dark areas in your SAR scene. So as you can see here, this water body, which acts very similar to a mirror, is extremely dark because most of the light that hits it bounces off of it and away from the sensor. So our next example is when a rougher surface like forest canopy is imaged by a SAR sensor. Reflections can bounce again off other objects and be redirected back towards the SAR sensor, resulting in a stronger return signal called volume scattering. In the case of volume scattering in a forest, leaves reflect radar signals onto other leaves and branches. Multiple scattering occurs until the signal exits the vegetation. A percentage of the incoming radar is therefore volumetrically scattered back to the SAR sensor, giving the vegetation a brighter signature than a smooth lake. So as you can see here on the right, this is an example of how a dense forest would be imaged using SAR. And then our last example is right here, and it's called double bounce backscatter, which occurs in areas like cities, where a large concentration of human-made features exist. In urban areas, the radar signal is first reflected specularly, or similar to a mirror, as you can see on this smooth surface in the bottom, and as it encounters roads and sidewalks. The specularly reflected signal then bounces off the sides of buildings, as you can see it doing as it bounces from the smooth surface and then off the building and back towards the sensor. Double bounce reflection causes most of the radar signal to return to the sensor, resulting in high backscatter and bright areas in your SAR scene. So down here is an example of an urban area that was imaged using SAR. As you can see, there are some dark areas which reflect the very smooth surfaces located in that urban area, but the bright areas are where buildings have reflected it directly back to the sensor. All right, so I'll go into some examples of radar monitoring systems. So Sentinel I is by the European Space Agency. The launch dates were 2014 for Sentinel 1A and 2016 for Sentinel 1B. The resolution is 20 meters, so this is relatively high resolution, and the temporal frequency, or the return period, is every 12 days. The cost is free, and we don't currently have products on Global Forest Watch right now using Sentinel-1, but there is an alert product in development that will increase the precision of our forest monitoring alerts. So the next topic we'll be talking about is LiDAR. So this is different from radar, and it's different because it uses a smaller electromagnetic wave as opposed to radar, which uses a long wavelength. LiDAR is more precise because of this. LiDAR can detect very small objects and a much higher level of detail. LiDAR is used in applications where the detection of an exact shape and size of the object is necessary. LiDAR data can be used to derive information about vegetation structure, such as canopy height, canopy cover, leaf area index, vertical forest structure, and even species identification. So how does LiDAR work? So LiDAR uses light sent out from a laser. Lasers aren't just for making your favorite band look awesome, reading barcodes, or removing hair. But how do they measure stuff like trees? A satellite contains the LiDAR unit, which scans the Earth, as you can see in the top right. LiDAR systems usually use either green or near infrared light because these types of light reflect strongly off of vegetation. The pulses of light energy travel to the ground and return back to the LiDAR sensor. To detect the height of detected objects, such as trees, the LiDAR system records the time it takes for the energy to travel to the ground and back. However, as you can see in this diagram, a pulse light doesn't just reflect off of one thing, like the top of a tree, and yield one return. A LiDAR pulse can travel through things like gaps between tree branches and leaves. Think about standing on the forest floor and watching sunlight filter through the top of the trees. Light energy that passes through the canopy reflects off of branches and trees within the canopy. LiDAR can travel through the canopy and record information starting from the top of the canopy, right here, and through the canopy all the way to the ground. LiDAR can help us understand what's happening inside the forest or the forest structure, such as the shape of trees, as you can see in the cloud point diagram on the right. And they can even detect whether there are shrubs below the trees on the forest floor. So the next part of this is going over an example of LiDAR systems. So the newest innovation in LiDAR is the Global Ecosystem Dynamics Investigation, also known as JEDI. This is a collaboration between NASA, UMD, and the country of Japan satellite. So the launch date was December 2018, and it was a 2-year project, which means now in 2020, we're receiving the first of the data from this project. The resolution is 25 meters. The coverage is between 51.6 degrees north and 51.6 degrees south. All JEDI products will be available for download for free. Global Forest Watch does not currently use JEDI. However, Global Forest Watch does intend to use biomass calculations derived from JEDI. All right, so we're moving on to the next part of the presentation. This final part of the webinar will cover how to access and interpret satellite imagery. We'll be focusing on optical imagery because that's what we primarily use on Global Forest Watch. So I'll give you some examples of different resources that you can use to access and analyze satellite imagery. For viewing satellite imagery, you can use Global Forest Watch's recent imagery tool, which we'll be demoing future, Planet, monthly mosaics available on Global Forest Watch, and Google Earth. For analyzing satellite imagery, you can use Google Earth Engine, SEAPL from the FAO, Collect Earth, and ClassLight. So some tips and tricks on how to analyze satellite imagery for when you do your own investigations. When you look at recent satellite imagery, pay attention to what has happened nearby. This is likely related to the changes that you're seeing in the vegetation. When you look around the landscape, you'll see certain changes in errors are more likely to happen along rivers, on steep slopes, and etc. This is due to the nature of how the satellite monitoring system is able to pick up imagery in these regions. Geography matters, so be aware of the country that you're looking at or the biome. Different drivers look different in different places. And then, of course, reference contacts with regional expertise. If you're looking at a region that you're not familiar with, especially in terms of geography, it's important to discuss what you're seeing with people who are familiar with that area. So here are some quick tips and tricks before we launch into our demo. So if the pattern that you're seeing in the satellite imagery is sparse and patchy, it could be fire, check for recent fires or burn scars. It could be drought, check for browning vegetation, or it could be a false positive. So make sure that when you're looking at something that has supposedly changed, that there actually is change or in the imagery. If you're seeing a pattern that's thin and linear, it could be a road. So check recent images to see if a road has been moving through this area. River, it's happening directly along a river. So this could be a reason for forest loss, and also a satellite error. So if it's random in the landscape, and this could be a result of a malfunction. If the loss is rectangular, you'll see possibly large-scale agriculture. So check recent images for that. And if you see small congruent patches, this could be small-scale agriculture. So next up, I think we're going to go into a demo. So I'm going to switch to a different screen. All right, so I'm going to show you the different kinds of satellite imagery that you can find on Global Forest Watch and that you have access to for free right now. So what you're seeing right here is an area in Pará, Brazil. What's pulled up right here are our default layers. So whenever you access our map, you'll see these layers. As we mentioned before, these layers are derived using Landsat imagery, and there are tree cover loss, tree cover gain, and tree cover data sets. We'll go into more detail about how these data sets are created in future webinars, but right now I want to focus on satellite imagery. So I'm going to click off of these using the X on the top right, and I'm going to go down to the bottom right. So we're going to look at recent imagery first. So these are satellite images that we've been able to get in the last month, and even the last couple of days, given the quality of the images. So right now you're seeing Sentinel II, which is an optical scanner. As you mentioned in the presentation, you're seeing a lot of cloud cover here. It's impossible to see all the way to the bottom. So what you can do is look at some different images. They'll be from different times of the year, but it's still within the month of January, so still recent loss. And then you can get a better image of that. You can zoom in and get a better idea of what's going on the ground. If you wanted to filter by cloud cover percentage, you can change it right here. Because this area is in the tropics, it's really hard to get a 0% cloud cover or a really clear image. So 25 might be the best that we're going to get in this region. You can also change the acquisition date. So you can look at 3 months in the past, 4 weeks, 1 week. So that's how you can narrow it down to the most recent time. And then also, as we mentioned before, you can do this really cool thing where switch from natural cover to vegetation health. And then I'm going to switch to a clearer image so you can get a better idea. So these bright red areas are where vegetation is healthy. And then these yellow areas are where there's vegetation that has been cleared. So this gives you a really good impression of what areas are really healthy and what areas are degraded just by looking at the contrast in the colors. So next up, I'm going to look at some other satellite imagery that's available. But last thing, I just wanted to mention that we have Sentinel II A and B here, as well as Landsat. However, for this region, it doesn't look like there is a clear Landsat image for you to look at. So I'm going to turn that off and then go to the map settings right here. So you'll see that there are a variety of different satellite images, and I'll just go through them real quickly so that you can see what the differences may be. So this is a satellite imagery that was collected using Google. So the data is from 2016, and so it's not as up to date as some of our other products, but it does have very high resolution imagery and can get a really good idea of what's happening in this area. Also, we have other Landsat imagery. This is less up to date as well and only goes to 2017, but you can look through the different years and get a broader idea of what's been happening in the region between 2013 and 2017. Lastly, we have planet imagery. As we said, this is the very high resolution imagery. We have it for every month going back to 2016, so you can see long-term change, as well as quarterly aggregations so that they can choose the best images for a quarter and compile them into one contiguous image. So now I'm going to kind of use some of those satellite imagery techniques that I talked about. Right here is a large mining operation. And the way that you can tell if you have any previous knowledge about mining is if you zoom in right here, you can see the distinct pools where mine tailings are being drained. These are the materials left over after the process of separating the valuable part of an ore. You can also get a better idea of this by using contextual data. So if you're not sure exactly what you're seeing, or you want to understand the legality of the tree cover loss that you're seeing, then you can use some contextual information. So we have some land use information here. And I'm going to turn on mining concession because I'm interested in knowing if this mining is legal, who owns this mine, what they're mining. So if I click right here, and it will show me that there is a mining concession here. It's symbolized in orange, and it looks like they're currently exploring. It's owned by this company right here, and it looks like they're mining for gold in this region. All right, so I'm going to move to a different example to give you another idea of what on-the-ground satellite imagery can look like and how you can interpret it. So this is another area in Pará. If you zoom in, you'll see that there are these really large areas of agriculture, possibly pasture. If you zoom out, it's really interesting. You can see an area of relatively untouched forest on the left right here and also on the right. So you may be wondering, why is there so much development in the middle here? What's going on in this indigenous territory right here? What's going on in this national park? So one way you can do that is, again, use contextual information. If we go into land use, you can turn on protected areas and see if these are perhaps areas where further development isn't allowed. And you would know that there is actually some areas here. There's a protected area on the left, the Floresta Nacional do Homocene, and then on the right here, the Terra Indígena Val. And then the last example I have for you is this area right here. This is also in Pará, and this is an example of a road that's cutting through forest. If you go into the satellite imagery tab over here, you'll see that this road has been here for quite a while. So we'll go maybe back to 2017 and see if it still exists. Yeah, so you can see that this road has been here for a while, but then you can ask yourself, is this road supposed to be here? What damage might this road be doing to the ecosystem? One way you can tell that is, again, using contextual data. So let's turn on primary forests. And you'll see that this road is actually cutting through some areas of primary forest as measured in 2001. So the extent of primary forest, which is this lighter green color right here, is being cut through by this road. And so that indicates that this primary forest, which is considered among the most biodiverse and crucial providers of many ecosystem services, is being possibly threatened by this road that's cutting through it. So that's everything from me. Thank you so much for joining us. I'm going to pass the presentation off to Alice, and she will lead our Q&A.
All right, thank you everyone for joining. We'll now open it up for a Q&A. So if you have a question, please enter it through the Q&A button. We'll pause for a few moments as you type in your questions. And in the meantime, I'd like to introduce Fred Stoll, the Deputy Director of WRI's Forest Program.
Good morning, all.
All right, let's get started with the Q&A. We'll have about 13 minutes to go through some of these questions. And if we don't get to your question, please feel free to reach out to one of us, or we can try to follow up with you after the webinar. So the first question is, can forest cover data in GFW be used as accurate data in a scientific publication, or is it an approximate fact? Michaela, do you want to take that?
Sure. Yeah. So yes, definitely the tree cover data that's on Global Forest Watch is published in Science in 2013. So it definitely is credible. It's used in a lot of different scientific papers. I think the important thing to understand is, what we've covered today is just about like the satellite images that are being taken from space. What we haven't covered yet, and will be more of the topic of our second webinar in this series, is how you actually go from those satellite images to creating some kind of data product, in this case, where tree cover exists. And so that's something we'll get into a bit more of the methodology in the second webinar.
Right, great. Thanks, Michaela. So the next question is, where do you get the source of information for the land use layers, such as mines, palm oil mills, etc., and how often are they updated? Kai, would you like to take that one?
Yes, so this is a very good question. So not all of our data is sourced using satellite imagery. These land use layers, such as the mines, palm oil mills, and et cetera, are sourced from a variety of organizations. We get information directly from national governments, such in the case of the mines layer, we have several data sets that we've compiled that are directly from Department of Mines in various countries. The palm oil mills, we work with organizations such as RSPO, as well as other nonprofits to get this information. And then we have a variety of other sources. We vet these data sets based on credibility, reputation, and any scientific and methodological documents that are accompanying them. So we do make sure that we put the most accurate data on our website. We try to update them as frequently as possible. So if we get an update in the mining's data set for Brazil, then we will incorporate this into our data set. So there is a variety of years represented in some of these data sets like mining, RSPO, palm oil mills, et cetera. You can learn more about them by clicking on the layer on our Global Forest Watch website and identifying the small I button on the top right. This will give you a full overview of the metadata for each data set.
All right, thank you, Kai. So the next question is, what is the reason that GFW uses optical imagery as opposed to radar or LiDAR? Michaela.
Sure. So part of that is just based on what is or has historically been freely available. So the Sentinel II satellite from the European Space Agency is relatively recent, as you saw, and that's really the first radar satellite image that or satellite sensor that has full global coverage. So it's actually, systematically covering the Earth on a every 5-day basis, and the images are freely available. So now that we have those freely available data source, we definitely want to incorporate that, and we're working on an alert system right now. But most of the data available on Global Forest Watch right now is based on, these data streams, Landsat and MODIS, that have been available and free for the last 10 plus years.
All right, thanks, Michaela. So the next question is, can we detect tree species using satellite imagery?
Yes, that's a good question. So there definitely are studies that do this at very local scale, often using, as Kai mentioned, using LiDAR or using more detailed, higher resolution satellite images. Since we're looking at a global scale and looking at, 30-meter resolution, which is not so detailed, at the global level, we're not able to pick up different tree species. And in fact, we're not really even able to distinguish different forest types, at least with the tree cover data that's on Global Forest Watch. We're just saying whether or not there's tree cover that's greater than 5 meters in height. So short answer is yes, it can be done, not yet at a global scale.
All right, thank you, Michaela. So I have 2 questions here that I think Kai can take. The first is, are all the data sets on GFW available for free and in formats compatible with QGIS? And also, is it possible to analyze the image in the GFW tool and then use it in ArcGIS or QGIS?
All right, these are very good questions. So most of our data sets on Global Forest Watch are available for free and are in formats compatible with QGIS. So to be more specific, a lot of our forest change data sets, which were developed by the University of Maryland, are available in raster format and can be downloaded on their website. We also have a link to this data on our open data portal, which you can access at data.globalforestwatch.org. And additionally, the question about whether, what was the second question? Oh yeah, so it is possible to analyze the image in QGIS or ArcGIS, but we don't allow the satellite imagery to be analyzed via GFW on our map. So again, as I said, you do have access to satellite imagery via our open data portal and via the UMD site, which we'll share. And then I previously mentioned on a slide all of the different areas where you can find free and open access to satellite imagery and satellite imagery analysis tools. So we'll send you the PowerPoint and you can review these resources for yourself, and they'll be very helpful.
All right, thank you, Kai. So the next question is, when will you have further products for LiDAR and radar to use in conjunction with the optical? And I'll hand that one over to Fred.
Thank you. I think that's a good question. The LiDAR and radar are so as Michaela explained, a bit new, especially the LiDAR, the jetting just became live 2 days ago. So now everybody can use the data. So now it will take some time to get it incorporated in our work. The same for the Sentinel data, you know, although it's 2 years old, it takes a long time to get it incorporated into a working environment that we can do global. But I would say expect in the next 2 years to really add new data into this optical satellite data that we have.
All right, thanks, Fred. Another question is, in regards of the use of planet imagery, are the monthly mosaics free to use? We normally make reports on deforestation and would like to know if I can use the planet images in our reports. So I'll hand that one to Michaela.
Yep. Great. That's a great question. So we have a special agreement with Planet where they've agreed to allow us to display the planet images on Global Forest Watch, or the monthly mosaics. So they are free and available to use on our platform for now, at least for as long as our agreement with them lasts. Typically, if you want to, use them in your own application or download them from Planet, you would have to enter into a separate contract with them. I will mention that the government of Norway recently put out a tender to purchase high resolution, frequent satellite images for the entire tropics that they're going to make available for free via Global Forest Watch and other monitoring systems. So we're definitely watching that very closely. I think once they make an announcement, that will be a very good resource for us and for everybody who's working on forests to actually have a reliable, free source of high resolution imagery.
All right, thank you, Michaela. The next question, which Kai will take on, is whether you can access the data and imagery through the GFW API.
That's a great question, and yes, you can. We have some guidelines as to how to do this on our developer portal, which is accessible via globalforestwatch.org. If you're having any trouble finding these resources, you can also reach out to me directly, and I can give you some guidance as to how to do this. You can also see that World Resources Institute and Global Forest Watch have a GitHub. So if you look there, you can also find some resources as to how to access this information.
All right, thank you, Kai. All right, the next one is, can we detect early forest fires by using LiDAR or radar?
Yeah, let me take that. Early forest fires, so I guess the question is if it's still a small fire. And indeed, like if you have our fire sensors currently are a bit rough, and so a small fire might not be detected that early. I do think LiDAR and radar will not improve that so much. I do think with higher resolution optical data, we actually will be able to see fires when they're very small, much easier and faster. Fires, of course, are hot, so it's very hot, and that with optical, you can see that heat index. So I do think we'll get better at that to the 30-meter resolution, so detect those fires earlier than we can do now. But again, it takes a little bit more development before we can do that. But I also expect that in the next few years to happen.
All right, thank you, Fred. So the next question is, which techniques do you use for generating forest loss data? And can we get access to the model and training samples? Is the model free to access? I'll pass that one over to Michaela.
Great. Yes, this is a great question. So in our next webinar, we'll actually be going over more of the details of the forest tree cover loss data that's on Global Forest Watch and how that was actually produced. So we'll get a bit more into the methodology. That data is produced by the University of Maryland, and right now they do not share the model or the training data, but we are working on a number of projects where we are expecting the code to be open source. So the radar alerts we're developing with Wageningen University, that model is going to be all freely available. We're also working on a land cover change project with Google and National Geographic, where we're creating a comprehensive land cover change data set that'll be training data that's freely available as well. So it's something we're working towards, but as of right now, that information and those models are not available publicly.
All right, thanks, Michaela. So being cognizant of time, we'll take one more question. Please note, if we didn't get to your question or you come up with another question, feel free to reach out to one of us or to our team, and we'll get back to you. So the last question is, how can you estimate the biomass in an area?
So we currently have a couple of layers on Global Forest Watch that do estimate biomass in an area. I'm going to share my screen just to give you a quick peek into those data sets, and so that you'll know where to find them for the future. So on our climate tab here on the left, you can go here and see that we do have several data sets that are looking at carbon density, such as tree biomass density, soil carbon density, carbon dioxide emissions from tree cover loss, carbon dioxide emissions from tree cover loss and drained peat. So these are all looking at above ground woody biomass in estimating the amount in certain regions. And these are global layers, by the way.
Great, thank you, Kai. So thank you everyone again for joining us. Please keep an eye out for our next webinar in the Frontiers in Forest Monitoring series, which will be intended to explore more in-depth remote sensing content. I noticed a lot of questions about when it will be planned for and if you'll have to register. It's being planned for late April and we will be announced on our communications channel, so please keep an eye out. And yes, you will need to register for that webinar as well. We'll be sending out a recording of this webinar, a copy of the presentation, and a brief survey to solicit your feedback. So please keep an eye out for that email. And again, if you have any additional questions or if we didn't get to your question, please feel free to reach out to one of us. Our emails are on the screen right now, or to our team at gfw@wri.org. Thanks everyone, and have a great morning or day or night, depending on your time zone.